series of sequences?
Not today. We'll talk a little bit about sequences today, but series is next class.
So speaking of sequences, is that going to be in our quiz?
If I get to it today, I might ask maybe a bonus problem on it. I think the next quiz I want to focus mostly on improper integrals and this stuff, approximate integrals. Just round off the last.
Speaking of improper integrals, like is it going to be like whatever we did on the last quiz, or after the last quiz on a little bit of improper integrals? Which one?
Well, remember the last quiz? In the bonus, I asked you about the convergence theorem, the comparison theorems.
Yeah.
Right. That's going to be a main part of the quiz now. So.
Okay.
All right. So last time, let's see where we left off. I think we started talking about Simpsons.
Yes.
So just remind you of the idea here. You had some curve doing its thing. You want to find out the error under AB, and the idea is the integral itself is very difficult to compute. So you want some way to actually approximate it. And so what you can do is you can dissect this guy. And what Simpsons does is it takes, all right, settle down now, pay attention. Simpsons takes 3 points and pretty much sketches a parabola through those points. And then it moves on to the next 3 points, then it sketches a parabola through those 3 points. And so it approximated the area under the curve by the area under this parabola. And we saw last time that this was given by, this part here was given by delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. And then if we looked at this part over here, this was given by delta x over 3 times, well, this one, f of x, x2 plus 4 f of x3 plus f of x4, and so on. And notice that now, if I were to combine these two areas, what's going to happen is my f of x2 appears twice, so that one kind of doubles up. And so that leads us to a general formula for Simpson's rule. So the Simpson's rule approximation, Sn. Was given by delta x over 3 is a common term, and then you're going to have the first y value 4 times the second y value, 2 times the third y value, and then 4, and then it alternates like that. And it ends with a 4. The alternation starts and ends with a 4, and then the last y value is not multiplied, right? So it's the first y value starting at the left end point, so it's the y value at the left end point. And this is the y value of the right end point. And in the middle, it alternates between 4 and 2 times all the y values starting at 4, ending at 4. Another thing that's very particular to Simpson's rule just by the way it's actually set up, you'll notice that to create these 3 points to get a parabola through it, we actually need to take up the space of 2 subintervals to get that to work. And then the next parabola is going to take up the space of 2 subintervals to get it to work. So each parabola requires 2 subintervals to get it to work, which means the way Simpsons is set up, you'll always have n must be even. Right? None of the other methods actually require an even number of subintervals, but Simpsons actually requires an even number of subintervals. Each parabola is going to take up 2 subintervals. Yes?
So you know how you draw 2 parabola, how'd you get 4f of x to the 1? Like how'd you get that 4?
Oh, well, we actually proved that last time. So the end of last class, I actually rushed through a proof where we actually computed the integral from a to b of ax squared plus bx plus c. Right? And I actually proved that the answer looks like this.
Oh, okay.
Right, we did it, rushed through that at the end of last class, right? So I actually proved that the error under each parabola is going to have this form, but now when you add up a bunch of those forms, it doubles up on the guys, on the intermediate guys, but the first and last guy doesn't double up, and so you end up with this kind of form.
So according to the handout, Siobhan,
Yep.
according to one of the handouts of the Simpsons rule, isn't it supposed to be like, so 2fx1 and 4fx2?
No, it always starts with a 4.
I mean, like, always starts with a 4, but
always starts
after
with a
the
4.
4, isn't it supposed to be like a 2?
Yes, which is what I wrote here. 4, then 2, then 4, then 2, then 4, then 2. So you stop at
Then how
4.
come it says 1, like, on fx4?
I don't know what you're talking about.
Like fx2, 4fx2.
Yes, fx4 in this example is the very last point, which doesn't have anything from it. Right? This is the xn in this example. So the first and the last guy does not have anything multiplying it. The intermediate guys do. Starting with 4, then 2, then 4, then 2, and all that. Right? So yeah, that's what gave you this formula. And so now what we're going to do is we're going to actually do some examples. Another thing, and I don't think they focus on this too much in the syllabus, they probably wouldn't ask it on the final, but can quickly run through this because the idea of knowing what these guys are is going to be important. So the list of formulas over here on the second page, this tells you the error estimates, right? So basically, an approximation is no good unless you know how good it is, right? Like, if it's approximating the answer, I want to know how far away from the actual answer is it, right? And that's what these guys are, right? So I'm not going to prove it to you, but we can know, it can be proven, that the error estimate for the midpoint rule, the trapezoid rule, and the Simpsons rule are given by these expressions, right? So E sub m is the error for the midpoint rule, E sub t is the error for the trapezoid rule, E sub s is the error for Simpsons rule. And basically it's saying the error will be less than or equal to this expression. So whenever you do one of these approximations, if you want to know worst case scenario, how far away from the answer am I, this expression is going to give you the answer, right? Now in this expression, you will tend to know everything. A is going to be the left endpoint, B is going to be the right endpoint, N is the number of subintervals, but there turns out to be this number K that's involved here. Now how you actually find out that K, I tell you right here. So for the midpoint and trapezoid rule, the K is just some constant that is an upper bound for the second derivative on the interval. While with Simpsons rule, you actually need more derivatives. It's an upper bound for the fourth derivative in absolute value on the interval. So when we go through the examples, you'll actually see how we apply those. But for now, let's actually just do some examples here. And
Do you have the handout from last Tuesday? So do you have a copy
no,
of it?
I don't have any extra copies. I gave you guys all the copies I have. So right now we're just going to jump into these. And I don't know, I think these examples are, I want to modify the examples a little bit. So first of all, we already went through the left-hand rule, right-hand rule, and midpoint rule in Calc 1. So I don't think we're going to need to worry about it now. So let's make this really focus on the trapezoid rule and Simpson's rule. So that's the first change. So pretty much every problem where I ask you to do something with the midpoint rule, just ignore that. We're going to keep everything with the trapezoid and Simpson's rule. The second thing, sine x for the first example is too easy. Let's do sine of 2x. It'll be a little bit more interesting. So, first example, we're going to look at the integral from 0 to pi of sine of 2x. Now, yes, I know you guys know how to integrate that and how to actually find the answer, but you know, it's the first example, so let's just keep it simple. So, let's pretend that we didn't know how to integrate this. We want to actually approximate what is that going to look like. So, let's actually use A, Simpson's, with 4 subintervals, and B, let's use trapezoid with 4 subintervals. So we're going to do some approximations of this integral. And just like with left-hand, right-hand midpoint rule, conceptually it's not terribly complicated. You're just going to plug the numbers into this formula and see what they are. So, let's do A. So, as always, the first thing you're going to want to do when doing these guys, and again, really kind of covered this in Calc 1, so I don't want to expand too much on this. But the first thing you always want to do is find delta x. Delta x is, what's the formula? B minus A over n. So, remember, your A is the left endpoint, your B is the right endpoint, and n is going to be given in the problem, right? So in this case, it is B, which is pi, minus A, which is 0, over n, which is 4. So your delta x is pi over 4. The next thing you're going to want to do, find the x sub I that you're going to be using in the formula. Now, I think it's nice to draw a little picture to actually do this. So normally I just draw like a 0, a pi to the A and the B. I want 4 subsections, 1, 2, 3, 4 subintervals. And basically how you start to find the xi, you would remember from another formula, that this is just A plus I delta x. I believe I also asked that on the last quiz. So you're going to start with the first guy, and then add delta x, then add delta x, then add delta x, then add delta x, until you get to the last guy, which is why knowing what delta x is in the first place is going to be important. So I just go, boom, add pi over 4, I get pi over 4. Boom, add pi over 4, I get pi over 2. Boom, add pi over 4, I get 3 pi over 4. Boom, add pi over 4, and I get pi, right? So the values here are the following: 0, pi over 4, pi over 2, 3 pi over 4, and pi. And that's your x0, that's your x1, that's your x2, that's your x3, that's your x4, which is the xn in this example. And so now, the third thing you do, apply the required formula. In this case, it's going to be Simpson's rule. So we want S sub 4. This is going to be an approximation for the area. This is going to be delta x divided by 3 times. Let's write it down. More space. F of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x4. Right? So you leave the first and the last y value, alternate everyone inside, starting with the 4. That's it. Now you've basically just plugged in. Our delta x was pi over 4. Plug that in, divide by 3, get pi over 12. And then I want f of x0, so that's going to be sine of 0 plus 4 times sine of 2 times pi over 4, because it's sine of 2x. pi over 2 plus 2 times sine of 2 times pi over 2, which is pi, plus 4 times sine of 2 times this, which is 3 pi over 2, plus sine of the last 2 times the last value, sine of 2 pi. That's it. Sine of 0?
0.
Sine of pi over 2?
1. No, 0. Oh, no, it's 1. Yeah.
1. Sine of pi?
0. 0.
Sine of 3 pi over 2?
Hang on.
This is minus 4. Sine of 2 pi?
0.
So, this approximation is 0.
Yeah.
Which in this case, that's the actual answer. Just kind of lucked out. That's basically the game. We're going to find delta x. We're going to find all the xi. Draw out a little sketch. Write how many subintervals you need. Start at the left-hand point. Keep adding delta x. And then you apply the right formula. In this case, we needed Simpson's rule. Questions? Yeah.
Oh, how'd you get pi over 2 from pi over 2?
Because it's 2 times the angle. So when I plug it in, it's going to double all of these guys. So 2 times 0, 0. 2 times pi over 4 is pi over 2. 2 times pi over 2 is pi. 2 times 3 pi over 4 is 3 pi over 2. 2 times pi is 2 pi. So I'm literally just plugging it into this formula. It's f of the thing. And in this case, our f of x is sine of 2x.
I think you're talking about the delta x over 3,
Yeah,
because you
how'd
went
you
from
get
pi over 12 to pi over 2.
So you forgot to put that.
Yeah, I think,
Oh,
yeah, it's 12.
yes. Other questions? And that's that. B, trapezoid rule. Same kind of idea. The first 2 steps are going to be exactly the same. It's just that step 3 is going to be different numbers. Let's just run through that again. B. So the trapezoid rule with n equals 4, you're given an integral you want to approximate. What we're going to do is first find delta x. Then I'm going to find an interval. Find all the subintervals. Here we have 4 dissections. Keep adding delta x. So here that's going to be pi over 4, pi over 2, 3 pi over 4, and pi. Then I'm going to find the trapezoid approximation with 4 subintervals. This is going to be delta x over 2. Plug in. Delta x over 2, so this is pi over 8. So now it's sine of 2 times 0 plus 2 times sine of 2 times pi 4 plus 2 times sine pi plus 2 times sine 3 pi 2 plus sine 2 pi. So that guy's 0, that guy's 0, that guy's 0.
Do we have to use the left-hand rule or the right-hand rule?
Use what's required. We're using trapezoid rule.
Okay, and then something about the Simpsons rule. Do we have to
That
use
was
like
part
left
A.
hand or right hand?
Neither. Those are completely different things.
Okay.
They're completely different things. Left-hand rule, right-hand rule, midpoint rule, they're completely different things. Simpson's rule is its own thing. Trapezoid rule is its own thing. So it's going to be essentially 2 minus 2. So again, your approximation is 0. Silly example, but I just want you guys to have the process down, right? So find delta x, find all your xi, plug into the formula. Get an answer. That's basically it. Alright, so now, problem 2, find the errors associated. Find the errors. So, A, the error for Simpsons, error for Simpsons. So the magnitude of the error is going to be less than or equal to what? Big K.
Parentheses B minus over 180 and so forth.
So now, the only interesting thing, or the only thing that you'd have to actually do some work on, is finding this K. Now, what is the rule for K?
Devon, according to our syllabus, you said omit error estimates. How come you're doing like in this? How come you said, in the syllabus they omit error estimates, whereas right now in class?
Oh, omit error estimates is more of an official thing, but I want you to be better than all the other classes. So I'm going to tell you things that's important for you to know, regardless of whether the math department wants us to admit it. K. How do you find K? So here, K has to be an upper bound for this guy on the interval, which is, in this case, 0 to pi. So, first thing we need to do is find the fourth derivative. Then what we're going to want to do, we're going to want to find a constant that is greater than or equal to the magnitude of the fourth derivative on that interval. So, our f of x here is sine of 2x. F prime would be f double prime. Double prime. And f to the fourth prime 16 sine 2x. So now you want the magnitude of 16 sine 2x to be less than or equal to k. Now, of course, you want k to be greater than or equal to this guy, but the smallest value that you can choose for k is going to be the best one. So you kind of want the smallest value that's greater than or equal to that. Otherwise, you might just overblow your error estimate. Can you tell me a good k to use here? What's the smallest number you can think of that's always going to be greater than or equal to that? 16. Right? Because this guy, the sine of 2x is always less than or equal to 1 in absolute value. Right? So 16 times this is always less than or equal to 16 in absolute value. Choosing k equals 16 going to be the best choice to pick. And so, Simpson's rule is an approximation. You are expected to not get the right answer exactly, but if you wanted to guess, well, what's the worst case scenario? How far off from the actual answer could I be? Then you'd say the error with Simpson's rule using 4 subintervals on this interval for the function sine of 2x. How far away could I be from the actual answer? Well, it's going to be 16, less than or equal to 16, pi minus 0 to the 5th over 180 n, which is 4 to the 4th. So this is how far away we can be, 16 pi to the 5th. 180. I don't know what that is, but. Computers is just for fun, like you don't have to know the exact answer. That would be how you answer the problem, that's the answer. But I'm just kind of curious as to what that is. Is that decimal? Let's see. So this is the error estimate. With only 4 subintervals, you're expected to be a maximum of that far away from the actual answer. So what Simpson's going to give you with this problem, you can expect it to be what the answer is plus or minus 0.106. And you might say, hey, that's good enough. Or you might say, that's not good enough. We need to increase n, and you'll get a better estimate. Right? So there are times when you can't get to the actual answer, but you can actually tell how far away you can get. And then you just decide for whatever situation you're in. Is that good enough? Yes. If not, use a bigger number for n.
So on the exam, if you write that the 16 pi to the 5th over that, is going to be the correct answer, or do you have to like find the actual answer like with the decimal like 0.16? Since we
Well,
don't have
this
to
is
have-
the actual answer. This is actually a better answer than that.
So if
This-
you
this I
write
just
the
rounded.
top one, the box one is going to be correct.
You're not going to have a choice. Like, you're not allowed to use a calculator. Right?
Yeah,
You're gonna
that's
figure
what
it
I'm
out.
saying,
Like, that's what you'd write. So, like, I use a calculator. I can do that. Come on. And look at B. Error for the trapezoid rule. Slightly different formula and a slightly different K. So how far you are from the actual answer with the trapezoid rule is going to be less than or equal to K times B minus A, what is that, to the 3rd?
Yes.
Over 12n squared. Now for the trapezoid rule, you don't need 4 derivatives. You only need 2 of them. So we want the magnitude of the second derivative to be less than or equal to k on the given interval. So your function was sine of 2x, your f prime is going to be 2 cosine 2x, your double prime is going to be minus 4 sine 2x. And so you need minus 4 sine 2x to be less than or equal to k. A nice k to choose for k equals 4. And so the error for the trapezoid rule in this situation is going to be smaller than or equal to 4 times pi minus 0 to the cubed over 12 times 4 squared. That's right. How does this compare to Simpson's rule? Who was better for this function? So this one's going to be off by 0.646. That one's like, yeah, yikes is right? That kind of makes sense though, right? The sine function is very wavy. It kind of lends itself to a parabola more than a trapezoid. So not really surprising here. So that would be what the trapezoid rule is. And again, you would choose this based on context. If you realize you have a very wavy function, Simpsons might be a better thing to choose than the trapezoid. But if you're in signal processing, a lot of times your function is very jagged and straight edges. Probably the trapezoid rule would be better for those. So for this particular case, if you only want to use 4 subintervals, the Simpsons rule is actually a lot better than the trapezoid rule. All right, so do problem 3. I'll give you guys 8 minutes. Maybe that's too much, 6. Try that one. We'll do it together. But conceptually, that's all there is to know about this section. There's nothing really to teach otherwise.
In the previous part, how did he get 180 as the denominator? How did he got that?
Oh, that's a formula. It's given on the second page. So do 3, then approximate with trapezoid rule. Run through a full problem.
k, that would be like, you know, the fourth derivative.
So for problem 3, you need trapezoid rule. So for trapezoid rule, you only need 2 derivatives. For trapezoid rule, you only need 2. You need 4 derivatives for Simpson's rule.
But they just publish it.
And the way you said
Yeah, so just yeah, so they already give you this value, which is 1 on 1. Then you just gotta figure out the rest of it. This is
About 2 minutes to wrap up.
2, 1 minus 2, so Q is just 1, give K over this thing. So essentially it becomes something like this, right? I don't, what do you guys get your K back? That's my question. I'm pretty sure I did it wrong. Was it 1, 6 or 6? I'm pretty sure I messed up with the question.
What are you doing?
Because you get the K for the caps. Because, I mean, question, did I do that? Am I supposed to be 1 half? Minus 1 half.
But I got that. Alright.
So that's what I think. Assume it was, I mean, X would be anything. I mean, the smallest problem is K would be 1, so I care. Right? Or, because I just say K was, I'm assuming, like, the smallest possible value. So when, so would that just be like, when X is equal to 6,
It would be 1.
goes 1.
That should be 1. Yeah.
So then that's what I mean, this would be 1 over 1 or 12 or something. So it's 100,
So
it's
this
10.
is X equals 1.
I mean,
So K equals 1.
is that what you want small? So if that's the case, that means this is equal to 10, and it has to be less than equal to 10. Because in this, now we have 1 over 100 times 1 over 12. No, I mean, you get the point, it's fractions.
No, you're just looking for it.
Yeah, but I mean, so this is the end of this, if it's 6, if it's 6, then it's the cube root of the square root. I don't know. Ridiculous.
Alright, let's do it.
It's a 1 over x, and 1 over something like that.
So, you want to approximate this guy?
I pulled up.
I didn't tell you the end, but I told you how I gave you a tolerance for the error. So you need to figure out how many subintervals you need to actually approximate this to be within that error on the trapezoid rule. What do we do?
You start by finding the second derivative.
First derivative is
Negative X.
second derivative.
Right, so you did some scale basically.
Or no, I just
So,
used the wrong.
now,
I didn't have x
I want the magnitude of 2 over x cubed to be less than or equal to k on the interval where x is between 1 and 2. What's the best k to pick?
2.
Why?
It's the biggest that you'll be.
So, our graph 1 over x on the right side, you should know, looks like this, which means it's decreasing. If I'm on the interval from 1 to 2, notice that the largest it is on that interval is at 2. 1 over, that's going to be, it's 1 over x. So x is 1, plug in 1, it's 1. What am I doing? This is supposed to be 2. This is, I'm graphing y equals 2 over x cubed. So notice that it is a decreasing function. So the highest value actually occurs at the beginning of the interval, and that is at 2. So choose k equals 2. That's going to be the highest point. If I choose something below 2, then there are points in that interval where the function is bigger. So k equals 2 is actually the good choice here. It's the responsible choice. So now what we're going to do, I know the error for the trapezoid rule is less than or equal to k times b minus a cubed over 12n squared. But now I know what my k is. 2. My b is 2. My a is 1. 12n squared. So that's the error. How do I get it to be within the tolerance that I want?
Simplify first.
That's going to be 1 over 6n squared.
So, I mean, it has to be less than 1 over 100, so I'd say...
Right, I want the error, so this is an expression that gives us the error. I want that to be better than 1 over 100. This is what we want. So, now you just solve that inequality. This means that 6n squared should be greater than or equal to 100, so that your n should be greater than or equal to 100 over 6 square rooted. Now, if that's an integer, that's good. If it's not an integer, what you can do is just take the ceiling function, round up. Let's see roughly what that is. Let's just see for this guy. It's like what? This says 4.1.
Yeah, you can round to 5.
So 5, I would choose 5. So if someone said, this is an integral we need to figure out, but we can't be more wrong than 2 decimal places because people are going to die. So what you would do is say, all right, set the computer to do for n equals 5. Now if you have the resources, you can go further, but if you can't spare the computational power, you can't spare the resources, 5 subintervals would be the responsible choice. I asked the follow-up to do it for 4, so 4 would probably get people killed, but let's just do it for 4 just as an exercise. So 5 would be the optimal number of subintervals here to make sure we're at least 2 decimal places to the actual answer. What would 4 give us? So let's actually find the trapezoid approximation with 4 subintervals. How do we do it? First find delta x, which is b minus a over n, which is b minus 1 over 4, which is 4. Then x of I. So we have the interval from 1 up to 2. We want 4 subintervals. How do I find the x of I? Well, I just keep adding the delta x. So I have 4 over 4 plus 1 over 4, that's 5 over 4. Plus 1 over 4, that's 6 over 4. Plus 1 over 4, that's 7 over 4. Plus 1 over 4, that's 8 over 4. That's the last guy. Then I'm going to plug into that formula. Delta x over 2 times f of 1 plus 2 times f of 5 over 4 plus 2 times f of 6 over 4 plus 2 times f of 7 over 4 plus f of 2. So this is going to be 1 over 8 times 1 plus 2 times 4 over 5 plus 2 times 4 over 6 plus 2 times 4 over 7 plus f of 2. And that's our answer. So usually I'll leave some instruction on the problem that says, oh, you don't have to combine the fractions. Like you can leave your answer as a sum of terms. This will be good enough for the answer. I'll assume you know how to do the arithmetic. You're not going to have to simplify it. So that would be the approximation. And this approximation might be a little worse than 2 decimal places. If I want to guarantee I'm correct up to 2 decimal places, I would have done 5 instead. So now what I want to do is I just want to start the next section, which just going to be an information dump at this point. We're going to talk about sequences. Now sequences, it's important, we need to know about them, but what we're going to learn about them is mainly to be of service in the next topic, which is series. So we're going to need to understand series from a sequences point of view. So what I'm going to do now is I'm going to tell you about sequences, what they are, and some important things that we need to know about them so that we can talk about series. And when we get to series, I'll tell you what those are. But for now, let's actually, but that's integration. That's everything we need to know about integration. So now we know all the techniques to actually compute different kinds of integrals. We know how to compute improper integrals, which is also super important. And we know how, if I can't compute this integral, how do I approximate it? Okay, good. That's all good stuff. We're moving on to 10.1. We're going to talk about sequences. So this is another phase of the class. It will involve integrals at some point, chapter 10, but integrals isn't the main focus. It's going to be a kind of a different mindset, but it shouldn't be too bad. So let's just jump into that. What is a sequence? A sequence is a list in a definite order. In this class, a list of numbers. So you can have technically a sequence of anything, but when I say sequence, we mean a list of numbers in a definite order. This is kind of a fuzzy definition. There are more precise definitions out there, but if you can understand a sequence as a list of numbers, you will be fine. So, for example, I can have a list, -1, 3, 7, 11. I can stop that list, so I can have a list of 4 things. I can think of this as a sequence. In fact, this is what I would call, because the list terminates, I call this a finite sequence. It's a list of a finite number of things. I can also have another list, say 0. And I can write ellipses. This guy here, this symbol indicates pattern continues. And so this is what would be called an infinite sequence. I can have an infinite list. Now, the thing is, when I was writing these down, I have a rule in my head. There was a definite sense of who should be next in this list. It's a list in a definite order. It means I was thinking of something when I was writing down these lists. Can anyone say what I was thinking of here?
Adding 4.
Adding 4. So start at -1 and add 4. That was the rule I had in my head. And the rule said terminate the process after you have 4 things. This is called a finite sequence. It is an example of something called an arithmetic sequence, which you would have learned about in high school. You would have learned about arithmetic sequences and geometric sequences. We're not really going to care about those here. Just want to know a sequence is just a list of things in a definite order. Anyone knows what this is called?
Fibonacci?
Right, this is called the Fibonacci sequence. Very famous sequence. People geek out about it all the time. Usually, if you have any quacks that think you can prove the existence of God with math, Fibonacci sequence is going to come up at some point. Because a lot of things in the universe follow this sequence. Fibonacci was actually studying populations of rabbits when he came up with this sequence. And it kind of tells you how rabbits repopulate. But, yeah, that's a very important sequence. You can look it up if you want.
Devon, Camilla copying it. The definite list of numbers and
A sequence is a list in a definite order.
definite order,
A list of numbers in a
a
definite
list
order.
of numbers
In a definite order.
in definite order.
Now, can name sequences, right? So I can talk about a sequence that I'm thinking about, but I can give it a name, kind of like how we can give functions a name. Almost exactly like how we can give functions a name, because we can actually think of sequences as functions. I'll talk about that soon. But we can name sequences, usually lowercase letters with subscripts. So, example, I can talk about a sequence A sub n. And I can tell you what the starting point is, and I can tell you what the ending point is. So here I can do the ending point, I can write up here. So, example 1 above. So if I was talking about this sequence that I just wrote down here, a finite list, I could say, this sequence I'm going to call AN. It's going to start at n equals 1. It's going to go up to n equals 4, because there are 4 guys in there, starting at the first guy, the second guy, the third guy, the fourth guy. And then I can tell you the rule that I was thinking of when I created. So I can say the sequence is defined by AN equals like minus 5 plus 4. So I can tell you a rule that I'm thinking of to come up with the numbers. I can tell you where that rule should start, where that rule should end. So the first number is going to be when n equals 1. Plug in n equals 1 into this formula, you get minus 1. Then the second number is when n equals 2. Plug in n equals 2 into this, you get the 3. Third number is when n equals 3. Plug in 3 into this, you would get the 7. Fourth number is n equals 4. Plug in 4 into this, you would get the 11. Right? So I can talk about a sequence, and then I can give you a rule that allows you to define that sequence. So oftentimes we'll define sequences in terms of formulas. I'll be able to talk about a formula that describes a sequence. And I can talk about a starting point and an ending point to let you know how the sequence, how long it is, how many terms there are. In example 2 above, the Fibonacci sequence, I can say I can call this one, say, B sub n, or F sub n, people like to call it. And I can say, and it starts from 1 going off to infinity. So you write infinity when you don't want to end the list. This means an infinite sequence. And I can say it's defined by B1 equals 0, B2 equals 1, and then Bn would be Bn minus 1 plus Bn minus 2 for n greater than or equal to 3. So this sequence, how it's usually defined, this is called a recursive definition. Meaning, the first few terms are known, and future terms are defined in terms of previous ones. So this is called a recursive definition. You should at least understand how it's made. So this is basically telling you the first guy is 0, the second guy is 1. To find all future guys, starting from the third guy onwards, you're going to just add the 2 previous guys. So the first guy was 0, the second guy is 1. Then you're like, what about the third guy? Add these 2, 0 plus 1, 1. What about the fourth guy? Add the previous 2, 2. What about the next guy? Add the previous 2, 3. Add the previous 2, 5. Add the previous 2, 8. And then, right? So it tells you these guys were initial values, these were given, and then you compute everyone based on those given values. Whenever a sequence is defined this way, we say it's a recursively defined. It's a recursively defined sequence. And that's it. So in the sequence, as you can imagine, this would be called B1, this would be called B2, this would be called B3, etc. These are called the terms of the sequence. So when I use that phrase, the terms of the sequence. So I can talk about the first term, the second term, the third term, the fourth term. So they're just named by the original letter, and then the subscripts tell you at what point in the list you are. So if I mention, say, B17, this is just the 17th term. So just the definition there. That's what I want to talk about. Now there's something important that we need to talk about for sequences. So that's what they are. This is how we write them down. Let me tell you another way to think about them first, and then I'll tell you about the important thing that we definitely need to know how to do with sequences. You have one job. When it comes to sequences, you have one job. You need to know how to do this thing. Okay. But another way to look at it first. Sequences are functions whose domain is the natural numbers, always the natural numbers. Now, some people might argue about whether 0 is a natural number or not. We're not going to have such arguments. We're calling the first guy number 1. But there are some guys who like to start their list at 0. The 0th term, the 1st term, the 2nd term, but then everything's kind of shifted back. But you think of a function whose domain is the natural numbers and the range is just the terms of the sequence. So if I'm talking about Fibonacci, I could just think of this as a function that takes 1 and maps it to 0. Then it takes 2, maps it to 1. Then it takes 3, maps it to 1. Then it takes 4, maps it to 2. Then it takes 5, maps it to 3. And then, or I can just think of it as a function where f of 1 equals 0, which means f of 2 equals 1, f of 3 equals so on, right? So you can literally think of them as functions. And when you think of them as functions, now you can start to draw pictures with them. Because, you have the xy plane, thanks to Descartes. And that will give you a lot of ideas on how to solve sequence problems. If you think of them as functions, certain things will be clear. In particular, the important thing that I'm going to tell you about now. Convergence of sequences. So when it comes to sequences, one thing you definitely need to know how to do is tell me whether a sequence converges or not. We say a sequence AN converges to a real number L. If the limit as n goes to infinity of the AN's formula is equal to L. No such L exists. We say the sequence diverges. This includes a limit of plus or minus You can get a limit, could be infinity or negative infinity, you will say it diverges. It converges if when you take the limit, you get a number, a real number. It doesn't have to be positive, it can be positive, negative, it could be 0, doesn't matter. You take the limit, you get a number, we say, oh, the sequence converges. And we can say the phrase an converges to L. So I can say, here's a sequence, it converges to 5. Basically that means, take the limit as n approaches infinity of an, all the terms approach the y value, the output 5. One thing is important, n equals infinity, always. This is always what you're talking about. So, why is that? Always take the limit as n approaches infinity of sequences. You will never approach any other number. So we may write, we might just write the limit of an equals L without specifically telling you what I'm taking it to, because everyone's going to know and understand it's to infinity. If it's a sequence, the limit is always infinity. Or sometimes write an and then arrow and L. So this will be understood when anyone writes it down. If I'm talking about a sequence and I write limit of the sequence is this, or the sequence arrow that, just means, oh, it's converging to that. The limit is infinity, and yeah, that'll be known. It does not make sense to approach any other number. And when you think of the function idea, that makes complete sense. So let me give you some examples of us talking about convergence of sequences. So here's the sequence. It is given by the formula an equals 1 over n. And someone can ask, does this sequence converge? Whenever someone asks you, does the sequence converge? You are always going to find the limit as n approaches infinity of an, which is going to be the limit as n approaches infinity of 1 over n, which you should know that is 0. And what is the picture here? This means if I were to draw a picture of what's going on. Notice that if I pick at 1, the output is going to be 1 over 1, so the output is going to be at 1. So that's that point. Then I can talk about what when n is 2, the output is now a half. I can talk about what about when n is 3, the output is now a third. What about when n is 4, the output now is a fourth, and so on. Right? Now, why is it that you cannot approach any other number? Well, you can't get close to any other number. If I take the limit as n approaches 2, what does that actually mean? It means you should be able to get arbitrarily close to when n equals 2. But there's like a whole gap of length 1. You can't get close to 2. Limit doesn't make any sense in that idea. However, what does make sense is I can look at the overall trend of the sequence. I can realize that all of these guys are following a pattern, and I can follow where they're going and kind of see where they end up. That makes sense. But to approach any limit in the interim doesn't make sense. Limits need to be able to get close to something. You will not be able to get close to any intermediate step in a sequence. So limit always as you go to infinity, never be anything else. Right? So that should be understood, and that's because they're really a sequence is a bunch of isolated points. I just tell you, on the integers, this is what the function is doing. Otherwise, the function does not exist. So it's only a function that has discrete values, you will call it. So this is an example of a convergent sequence. So I could actually answer here, yes, an converges to 0. And what converges means? Follow the overall trend. Let's do another example. So that's basically it. A sequence converges, that's the thing you need to know about. And basically it's like you finding limits, which now goes without saying. You need to remember all your limit rules from Calc 1. I'm going to expect you to know all of it. L'Hopital's rule, squeeze theorem, all that good stuff. If you don't remember, you can watch my Calc 1 videos, but I'm going to expect you to remember everything about limits, because when it comes to sequences, knowing about convergence is finding a limit. I define a sequence by n. Right? So this guy basically means when it's 1, the output is 1. It's 2, the output is 2. It's 3, the output is 3. It's 4, the output is 4, and so on, and so on, and so on. And I can talk about what is the trend. Does this sequence converge? Right? So what I can do is I can find the limit as n approaches infinity, which I'm not always going to write, but it's going to be the limit as n approaches infinity of n, which we know is infinity. And so what I would say is an diverges, because that is not a real number. You could say diverge to infinity, but I'm not going to care that you're so specific. Just tell me something diverges, and I don't care what it diverges to. It's not going to be good enough for our purposes, right? And diverges. This is a divergent sequence. It goes to infinity. I can give you another example. This is a kind of expression that's going to be very important to us moving on into the future. Minus 1 to the n. Now, basically what that means is now you're plugging in integers. Plug in n equals 1, then n equals 2, then n equals 3. You'll notice that every time n hits an odd integer, it will return -1. Whenever n hits an even integer, it will return +1. This is going to be, therefore, the standard way in which we kind of model alternating signs. We're going to look at things that alternate signs. Like go from plus a positive something to a minus something to a positive something to a minus something. It's a very important kind of thing to model. So -1 to the n, that's what it means. It just bounces up and down between -1 and 1. So I can talk about, does this guy converge? Well, I have a function. 1, 2, 3, 4, 5. And we can know that 1 is going to be the maximum this guy's going to hit. And -1 is going to be the minimum that this guy is going to hit. And so what's going to happen is 1, plug in n equals 1, will get you -1. 2, plug in n equals 2, gives you +1. And then 3, -1. 4, +1. 5, -1. And it does that the whole time. Right? So the trend that you're seeing is you just have this thing called an alternating sequence. It's just bouncing between two nodes, just jumping up and down. And so if I say now, what is the limit of an? Well, this is just the limit, -1 to the n, which is, does not exist. Because remember what a limit means. It means there's an output that we're always getting closer to as we go on. There is no such number. Are we getting closer to 1 as we go up to infinity? No. You'll always have another guy who's really far away from 1, at least 2 units. Right? Every guy that hits 1, the very next guy is going to be 2 units away. Not good enough for a limit, so that does not exist. I can say AN diverges. To understand the idea of convergent divergence. Okay. So sequence, a list and a definite order, we can think of them as functions. We can describe them with formulas, and we often want to know about the convergence of sequences. We're going to see why this is important when I start talking about series. And when I talk about convergence, it just means that you're taking the limit as n approaches infinity, always infinity. There will never be any other limit. So now, I'll just remind you of, not going into detail, remind you of some things, limit properties and some limit rules that you should know. So this applies to convergent sequences. Just so you know what's legal, what the rules are, CA constant. These are things you can assume will work out algebraically. 1, if I want to find the limit of a constant times these terms, you can factor constants outside the limit. So the limit of a constant times a sequence is the constant times the limit of the sequence. 2, when it comes to sequences, limits do distribute across sums, so you can assume that you can separate the limit when there's a sum. 3, limits distribute across products. Whenever they're convergent, they have to be convergent. If these guys diverge, then all bets are off. These can all break. But once each individual limit is a number, it turns out it maintains all the nice properties that you love about limits. The limit of a division of sequences is going to be the limits of the sequences divided, provided, of course, the limit of the Bn is not 0. Limits can move into powers. So if you have the limit of a sequence raised to a power, it's just the limit of the sequence raised to the power. And your k is positive. You don't want to have to worry about 0. So limits are very nice, algebraically speaking. They distribute across everything. That was in Calc 1, and the same is true here. Yes?
For example 3 of the limits, so say you have like the AN and BN is supposed to represent 2 sequences, right?
Yes.
So like you have like, let's say AN is divergent and BN is like, we don't know. If we split it up, oh. Okay. But like, if one...
If one of them is divergent,
Yeah.
you cannot assume anything here holds.
Oh, okay.
You'd have to verify case by
Alright.
case.
Thank
Yeah, there's no, I can't tell you in general what's going to happen. But if they're convergent, this will happen in general. It's definitely going to work out. So I can have sequences where they diverge, and sometimes it'll work out, sometimes it won't. So, for example, if I have AN is a 0 sequence, and I have BN is the sequence where it's always outputting 1, and I have CN is an alternating sequence, then it turns out that AN-CN converges, but BN-CN diverges. Right? So it can go either way. The product can work out or it could not work out. You don't know. It depends on the situation. But if everyone converges, then the product is always going to converge. So, but my AN was always 0, my BN was always 1, my CN is 1 over N, then AN, BN is going to converge to 0, AN, CN is going to converge to 0, BN, CN is going to converge to 0. Yeah, they'll all actually converge. So once each individual converges, the product is going to converge. It's always going to happen. If someone diverges, the product could converge or it could diverge, case-by-case basis. You can't say any of these are true in general. For convergent sequence, these are true in general. So we'll stop there. We'll pick up on Tuesday. So the quiz on Tuesday, I think, would be, I'll ask you about some improper integrals where you're going to have to use the comparison theorem. I'll ask you about, of course, Simpson's and trapezoids rule. And I'll ask you some basic things about, does this sequence converge? In the bonus, I'll probably ask you about using an error estimate, and I'll give you the formula for it so you don't have to remember the error estimate formulas. As well as, maybe I might ask something about series integrals.
Series sequences, but speaking of the rules, so do you remember every single quiz we have like rule questions? Rule questions.
In terms of rules, I'll probably ask you like state the formulas for Simpsons and trapezoids before applying them. I'll probably ask you to write down the trapezoid rule formula.
Well,
write
is
down
there
the
going to be any rules on the conversion and diversion on the theories and the sequences?
I don't think I'd ask that, but
But I'm talking about the rule part.
rules would be this actually. So if I were to ask you rules on sequences, I would ask you something like this. Like, can you state the properties of convergent sequences?
But nothing like, the definition of, we say a sequence AN converges to a real number, or if a limit of AN equals to L,